Palaeontology is using the electromagnetic spectrum to unlock dilute traces of life from deep time to help resolve the shape, structure, chemistry and biology of life on Earth. Some facets of the spectrum are familiar to us, such as X-rays, usually conjuring monochrome images of broken bones. The energy from the Sun and other objects in the universe travels to Earth as electromagnetic waves. All of these waves travel at the speed of light, 300,000 kilometers per second in space. Although the waves travel at the same speed, they may go up and down quickly, a short wavelength, while others go up and down slowly, a long wavelength. Long wavelengths have low energy, while short wavelengths have high energy. The combined wavelengths form the electromagnetic spectrum. It might seem strange when watching dinosaur bones being excavated from the ground that the electromagnetic spectrum can play an important role when studying these fossil remains, both in the field and in the laboratory. LiDAR images emit a pulsed beam of near-infrared light that is backscattered by target objects and recaptured by the scanner's detector. Thousands of scanned points combine to provide an accurate 3D point cloud of the surveyed landscape, or even a dinosaur. One of the largest dinosaurs in the world, Argentinosaurus, has been scanned this way, using a high-resolution, medium-range LiDAR imager. The resulting point cloud generates a 3D skeletal model that can be used to calculate the volume of the dinosaur. This in turn enables us to estimate body mass, a crucial parameter used to constrain the biomechanical and physiological traits in both extinct and living organisms. 3D bone models can also help us understand the maximum body mass such limbs might have withstood. A velociraptor hand claw holds many secrets that only high-power X-rays might reveal, generated by a laboratory microtomography unit. Slice by slice, the X-rays reveal the internal microstructure hidden for over 70 million years. The scan data enables an accurate 3D reconstruction of the claw to be made. Even breaks in the bone can be digitally mended. The mended claw can then be repaired for a virtual test, complete with digital claw sheath and physical properties for each material, allowing a finite element model of the whole claw. This model can be virtually brought back to life using some of the most powerful supercomputers in the world, allowing the velociraptor claw function to be quantitatively analyzed for the very first time. Not only do we use lab-based X-ray sources to help drive our paleontological and materials research, we also use synchrotron radiation. This is the brightest light in the universe. One such synchrotron is the Diamond Light Source in the UK. It works like a giant microscope, harnessing the power of electrons to produce X-rays brighter than 10 billion stars. This can be used to study anything from fossils to jet engines and from viruses to vaccines. Let's take a look inside and see how it works. With the roof peeled back, let's see where the electrons that generate X-rays start their journey. Electrons are generated by a particle source, such as a radio frequency ion source. A linear particle accelerator fires the particles into the booster ring, where the electrons are accelerated to just below the speed of light. They are then injected into the outer storage ring, with the particles being constantly guided and accelerated by a series of powerful magnets. When such high-energy particles travel at relativistic speeds, synchrotron radiation in the form of intense X-rays is produced, guided and then focused onto the subject of the experiment. Here, the iconic fossil Archaeopteryx gets bathed in synchrotron-generated X-rays that yields high-resolution data on elements that compose our fossil. Working at the Stanford Synchrotron, we were able to map the chemistry of each feather, permitting a glimpse of the plumage patterns of this 150 million-year-old bird. The distribution of key elements such as copper, nickel, and sulfur allowed us to reconstruct this early bird, albeit in monochrome plumage, as colour is still too complex to confidently refine from fossil feathers. The application of the electromagnetic spectrum to life on Earth has many more facets to explore in our X-Appeal exhibit. So join us at the Royal Society's Summer Science Exhibition, where you'll come face to face with a predatory dinosaur whose painful secrets might only be a mere wavelength away.